All right. Hi, my name is Cheyenne Yoakum. I am the team lead for the AUV track for Dynamic Systems. Other things that I'm involved in on campus are the Society of Women Engineers and the WISE Mentoring Program.
I'm Livy Jurens. I'm involved in the Women's Track Team, Student Senate, and the International Society of Explosive Engineers.
Hi, my name is Kaiden DeGrosse. I'm a fifth-year mechanical student, and I'm involved in the soccer club, peer mentoring, Biomedical Engineers Society, and the ASME Society as well.
My name is Travis. I'm also an ME, and I'm an RA on campus, and I'm also on the Hard Rocker track and field team.
My name is Asher Escom. I'm involved with being a tutor on campus and the Hard Rock and Drama Club as the tech director.
Awesome. So our track is working on the REMUS 100 specifically. It's the basic model for the Remote Environmental Monitoring Units. It's a compact, lightweight, autonomous underwater vehicle designed for operation in coastal environments up to 100 meters in depth. It can be configured to a wide variety of standard or customer specified sensors and system operations to meet unique autonomous mission requirements.
So some of the public health and safety and welfare things that this deals with are oil spills, dive rescue, like in underwater caves. They are low risk, so they're taking people out of the equation, so it's a lot safer. One thing they're used for is black box search and recovery in plane crashes, debris field mapping, and harbor security.
Some global, cultural, social, environmental, and economic impacts that this project could have include underwater surveying, seafloor mapping, Iraqi freedom. A similar type of mechatronic system was used to do underwater surveying. I'm sorry. Underwater mine detection for Iraqi freedom. And as Livy said, this type of robot might make divers obsolete.
It also changes things for marine life tracking, for if you're following things like pods of whales or looking at other endangered species. If you track them, this sort of system could be something that follows them and learns more about the habits of them. And then fishery operations would be made easier. It's much less expensive to have a system like this than it is to hire out a research vessel or an entire boat of scientists and use their time. It helps with underwater detection and building things like sonar grids so that large boats going through kind of less mapped areas can kind of know what they're getting into. But a kind of negative of that is that making ocean floor access easier possibly increases and promotes human interference with that, and could have a negative impact on the environment of the sea life down there and on mineral usage through the ocean floor.
So here is our very basic preliminary block diagram to way we think this works without a ton of research. We have 4 different inputs. We have a pitch input, a yaw input, and a roll input that are then all looped back to keep monitoring themselves, as well as a current velocity input if the device is already moving. Those all go into summing junctions to our error signal that will then be input into the brain of the device or the microcontroller. And that gets outputted into the motor functions, which will then either change pitch, yaw, and roll or velocity. And that also gets feedback into the error signal, just so it keeps track of what it's doing. And the final output, X of S, should be a translational movement.